Hello everyone, I'm Ashutosh. I'm going to talk about what's new in Apache Hive. Hive 3.0 just released last month. So there's a lot of new exciting features in that. Do realize that I'm the one who's standing between you and your lunch, but I try to keep you in this room till 12:30. All right, so let's begin. So before we talk about what's new, let's just look at how it all started. Let's take a peek at the distant past. So Hive started as basically a read-only engine to do a large batch processing queries. Initial engine was MapReduce. HiveQL was the language, which has a lot of features which are specific to Hive. This started in like 2008. Since 2008 to 2013, we did a lot of batch processing. Starting at about 2013, we started to take Hive beyond its batch processing roots. Some of you may remember we have a Stinger initiative which started like in January 2013. The first of some of that work went in Hive 0.10 release. That was in 2013, and now we are at 3.0, which was released last month. So in this subsequent 5 years, a lot of work has happened to take Hive to the next level. Mostly along 4 different axes, as I have here. In the runtime, we first started with a new runtime engine, Taze, which allows us to do the DAG-based query processing. We had a lot of improvements in the compiler which went in as well. In this duration, we have a cost-based optimizer which can now reason about the cost of the different plans and choose the best one. We have a lot of improvements in the SQL support. And last but not the least, we have made a lot of progress into the transactional capabilities in Hive. Now, basically, you will have asset support where you can do update deletes with the snapshot isolation. So that was so all of this work has basically led us to this place where now Hive is capable of executing nearly all SQL queries, not nearly, but all of them from the TPCDS suite. We have our own in-memory cache in LLAP, which provides us very low latency access to the data. We have asset merge support. We have, and this is like just for performance and the features, but we are also enterprise ready. So we have security. Hive exposes these endpoints through which you can enable row level and the column level security. You can do the replication for your disaster recovery. We are compatible with most of the tool vendors. All of them speak SQL, BI especially, and of course we have proven at the large scale. So these are like some of the facts which are applicable in Hive. So these are not the things which Hive is capable of doing. It's actually what it already does. I mean, I've personally seen these numbers at the customer and user sites. So we can do like 100,000 queries per second, mostly because of the lot of work which has went into the Hive Server 2 scalability and LLAP scheduling. 100 million rows per node, that is the vectorization work which has happened, which has made this possible. And of course, thanks to Hadoop and HDFS, we can scale to very large data sizes with 4,500 plus nodes and 300 plus petabyte storage. And if that is not enough to convince you how far we have come along, we also got a validation from the research community, which last week Hive actually won the Sigma 2018 Software System Awards, which put us in the leagues of Postgres, SQLite, and MongoDB. I mean, these are one of the best systems out there. And quoting from there for developing seminal software systems that serves to bring relational style declarative programming to the Hadoop system. So I'm pretty pleased with it. This was Sigma in Houston last week. All right, so this was the peak in the past, but what's coming in 3.2 is this. This is like a summary slide which captures the most of the important features that we are shipping in, beginning from the storage all the way to the serving. So let me begin from the left. So the asset system, we have revamped it, and now it's we call it asset V2. It has a ton of enhancements. I will talk a little bit more about it in the later slides. This allows you to, of course, make it use the Hive as a data warehouse engine with transaction guarantees. We have materialized views for to improve performance. A lot of changes has went into the compiler with the statistics and the constraints and so on to make this more useful. No more manual tuning of the queries. Materialized views can do the automatic rewrites if you have them. Workload management to allow even more parallelism in your during your execution, as well as guardrails. So the queries which are authenticated but are runaway, you can keep track of them and keep a tab on them as well. And last and not the least, all the way to the query result cache. So if you have the same query, and you get that repeatedly, and this happens quite a bit in the BI kind of a workload, where there are analysts who are sitting in front of Tableau or MicroStrategy or those tools like those, and they usually do the same set of operation when they start their slicing and dicing. So count star on a table and so on. So these kind of queries are pretty repetitive, and we now have a feature to cache the results, the result set of those queries, and can directly answer from them. And it actually skips the whole of the compilation and planning itself. So this is pretty fast. So all of these features are gonna make Hive ready for what we call as BI. I mean, it's already people are using it, but now it's actually gonna be further ahead. So how did we get here? So we have all these features. As I talked, there are multiple different axes where we made progress on. In the runtime, we have LLAP, of course, you know about that. So I'm going to talk about these things a little bit more in the subsequent slides. But at the high level, there are three different components of the system. With the planner, we have a CBO, and on the storage side, improvements in the asset. So let me begin with the materialized views. This is coming up quite a lot. So just to give you the little bit motivation of the problem and why is it useful to solve this. Once you have your workload and you have a handle on what kind of a queries you are running and what kind of a data set that you have, the way to, and then once you have exhausted your configuration, tuning and all of that, the way to next level of improvement that you can do is you can start thinking about how can you change the data layout on the file system so that you may, for example, may use SMB joins and so on. How can you materialize the queries so you can do the filter, you can do the aggregations, pre-aggregations, so that you don't have to do that at the runtime. So this is possible. You can do this manually, but this is pretty brittle. First of all, you have to figure out what views you want. You have to create them, and then you have to tell the users to rewrite their queries to use these views. And then these tables, they may go out of sync from the source tables, and then you have to have a problem of keep them up to date. So that's where actually the materialized views come to the rescue. I'm assuming some of you are already familiar with the terms, so it's not a new thing. But what it allows you to do is to basically define a query and store its result set into the system. So, and then the future queries which are on those tables, we can rewrite them using these views, so that there is no need to change in the query themselves, in the query text themselves. So we have support for aggregates, we have support for joins, projections, filters, and all of that. Any of those query patterns, you can create a view, and we can do the plan matching at the runtime. We also allows the rewrites against out-of-date materialization, what that means is that system keeps track of what changes are going into the source table, And if it is out of date, depending on how have you configured, it will decide not to use the view, or it can use the view and generate a compensating query from the new changes which are kept separate in the delta files and still answer the query, so which may still be faster. So all of that is behind the scenes. Users need not to worry about that. So that is all possible. Sorry. So the views in Materialized in Hive 3, you can have multiple ways to store them. You can have them in, of course, in LLAP. You can write the results back and store them back in the LLAP, which ultimately goes into the HDFS. Or you can use them at Druid. So Druid is basically this fast group by engine, which lets you do the aggregations at a petabyte scale pretty fast. So most common use case of the views is that you denormalize your tables. So you do all the joins. If you have a star schema, you flatten it out and then store that denormalized table as a view, and so that you don't have to do any joins when the query arrives. But then you change your filters and you change your aggregates, and then you use that view in that fashion. For that purpose, Druid is pretty good. So we have done the work to make that happen. And yeah, there are multiple options for user to control how the views are used and discarded in the whole life cycle of it. So just to give you a quick example here. On the right side, you can see that it's a typical TPCH schema. You have a line item in the center of your star, and you have a part, supplier, customers, and data. So as I said, in the most common scenario, we basically do a join. You flatten that table out. So you create a materialized view. You store the result of that join, all the projections that you want from that join table. And then in the later time, you get a query select some expression on which just to do a join between two tables. Now, as I earlier talked about the constraints, so we know that there is a PK-FK relationship between these tables, so it will not change the cardinality of the data. So we can still rewrite the query using this view, although we are not using there is no join the query with other tables. And then we can also match the expression, so we can do the aggregation on that of that expression, which we already computed in the view. So this basically turns this from a join into a scan, and this will gets you a lot of performance at the runtime. A little bit about how to maintain your views. If the view was out of date, we basically have a mechanism for user to manually run the alter table, which will rebuild it. And when you run that alter statement, it's not going to do the full rewrite of or full computation of the view and then store it back. It actually will. It's smart enough to figure out if what has changed in the source table and do the computation only on the top of those changes. And this is made possible because in our asset systems, we have separate delta files where we know the new changes which are coming in, and they are kept separate till the compaction happens. So we can do these changes. We can do these rewrites pretty easily, and this also allows you to. The same mechanism also allows you to use the views which are already out of date, and then use them for answering the queries with the compensating queries on top of it. So there are more details for this topic. There is a full talk, I think today itself, by Jesus. So please go join that if you are more interested in this topic. So the next item is workload management. So the workload management, the goal is basically to share this large LLAP cluster where you have a lot of different users who are running different kind of workloads to effectively pool their resources. In LLAP pools so that they can use this cluster. And also to provide guardrails. You may have a query which is allowed by the system to run, maybe coming from the some user, but now it's gonna do like a large scan on all the tables which are out there. So you want some mechanisms to protect your cluster against these queries. So there's a guardrails against that which you can define. Now, since these all of this resources are now pooled together in this cluster, the schedule, the LLP scheduler has a better view of the system. So it can exploit that to do the better scheduling. For example, it knows which applications is coming in and what's the priority of that, and to route to which queue and so on. So it also helps there. So let me give a quick example of that. So essentially, the central concept in the workload management is a resource plan. So you basically create a resource plan. You tell the system how you want your resources to be divided up and who's allowed to use them, how much of them, and when to kill the queries if they don't follow the rules. So in this example, I have created a resource plan called daytime, which can be applied between any duration. So in this case, I say that it will be applied during business hours. I have two pools in it, BI and ETL, and have divided up that as 75% and 25% between them, and I allow 5 and 10 queries respectively. Then I add a rule into the BI pool, which says that if the total runtime of any query exceeds more than 120 seconds, downgrade it to then move it to the ETL essentially. So it will basically move those query, which is a runaway query from the BI query to the ETL, BI pool to the ETL pool. And then you can also also do the routing of the query. So if you say that, you can say that route all my queries which are coming from the Tableau into this particular pool. And you have a choice to do the default pool if you don't know where it is coming from. So this basically is the new syntax which will be in 3.0, and using this you can effectively divide up and control the usage of the resources. So it has a concept of guaranteed tasks. So let me actually go to the example. It's easier to, yeah. So in this example, let's say I have two pools, BI pool and the ETL pool, and I have 18 total executors in the system, out of which I have allocated 80% of my queue or 80% of my resources to the BI and 20% to the ETL, which means 14 tasks and 4 tasks which can run in these pools. So then I get a query in the BI, and let's say it's asking for 10 active tasks. So basically I planned a query, I got a query in the BI pool, I planned for it, I got 10 active tasks. So I will run those tasks in these 10 guaranteed slots, we call it, because it's a minimum capacity which is reserved for this pool. And then there are 4 which are unused as of now. Then second query comes into the system, it goes to the ETL pool, and then it's planned, and it comes up with requirement of 19 tasks, right? So from these 19 tasks, we have only 4 slots available because that's all was allocated to it. So we run those guaranteed slots, we assign those guaranteed slots to this query. So it has 4 of them running. And now it has like 15 tasks which are still pending. So at this point, we can speculatively go and do the work stealing from the other queue which has those 4 slots available. We use them and then run the queries. At the same time, if something else comes into the BI queries, those 4 slots will be taken back. They will be, the ETL query will be preempted, and we can make a forward progress. So, so this is workload management. This works hand in hand with the caching. So let's quickly go over that as well. So caching for BI workloads, basically in LLP we have a columnar cache. So we basically do the unit of or the granularity of the cache is basically one stripe, and this is important because in data warehousing you usually have like wide tables because of the denormalizations people have performed, and then it doesn't make sense to cache all of the columns, right? So you want to have the heavy hitters, and then also you may have only few rows out of this, right? So you do not want to cache everything. So we are smart enough to do that. We can figure that out from the access patterns. And then in the cache, there are like different priority levels because there are indexes with each of those associated with those column vectors. And we want to cache them in the higher priority because they allow us to do the pruning of these stripes. So we can skip scanning all those row groups in one go. So, so we have that. And these caches are actually, this data cache is actually off heap, so there is no GC collection or pauses anymore. We support SSD. We have LRFU replacement policy to figure out which data remains in cache and which is kicked out. The ORC and Parquet are columnar formats, so they are cached natively. The new stuff that we have done in past few months is also to add support for the text-based data, like JSON or just plain CSV files. The way it works is that once the first time when the query comes in, we will serve it from, we'll read it from the disk, we'll serve it from there and then do the processing, but at the same time we will, in the background, we'll encode it so in the columnar format so that for the subsequent queries we can use it from the cache. So this is like a high-level architecture for how the cache works. We basically have execution threads and I/O threads, and the execution thread is doing this columnar processing on the data. So fragments is basically a query fragment or a plan fragment, which has a bunch of operators pipelined, and it is receiving these column vectors from the I/O threads and processing on them one vector at a time. When it runs out of that vectors or data to work on, it requests from the I/O threads to more data. At that point, the I/O thread will look in its cache. If it is there, then it will give it to the execution thread. One more thing I want to highlight is that this data that we are caching, it is decompressed but still encoded. So that doing it, having it decompressed helps in lowering the costs of the CPU utilization, but having it encoded helps in improved memory efficiency, because decompression is a CPU heavy operations, but encoding is light on CPU, but it still gives you the space conservation. So yeah, so we have a decoder thread which will do the decoding and provide that to the execution thread if need be. And yeah, we also have a SSD cache where we can have offloaded some of the heap, some of the cache from where we can go and look it up if it is needed. So this is about the caching and the LLAP. There is actually if you want more details into this thing, like how we have improved the system from the runtime perspective, there's another talk tomorrow by Neeta, running Hive queries fast in the cloud. So check it out if you are more interested in these topics. Now we come to the improvements that we have done with the Druid. So I briefly mentioned Druid in context of Materialized view earlier. Even outside of Materialized views, Druid is a system which is used quite a bit with Hive and without Hive. It basically, as I mentioned, is very good for lookups, point lookup queries, or doing an aggregation on these large data set. So in 3.0, we have made some improvements in this story. We have now actually are able to push down much more complicated expressions compared to earlier. So why is that? Why from where these complex segregation expressions are coming from? Just to give you a context, many BI tools like Tableau, for instance, they have like a common denominator of the queries that they will generate, which any target engine can execute. So even if you have a date, let's say if you have a timestamp column, and you have declared it as such, what Tableau will do is it will read that timestamp, it will apply a function to extract year out of it, will treat it as an integer, and month extract from it, treat it as an integer, and then will do its own date time arithmetic on top of it, instead of using the functions which are already supported first class in the SQL engine. So because of that, these expressions can get really, really complicated. And actually, I saw one query from Tableau actually, which was like megabytes of query, which only thing which it has was these expressions, nothing more. So we have done a lot of work in that area. So now we can much more, and since it's a time series based system, Druid, it makes sense to push down those queries there. We of course can store the materialized views in Druid, which helps you to do the slicing and dicing use case. And it's not just Hive which we are improving here, it's also Druid. So Druid till now didn't had a clear semantics on the nulls, which is compatible with the SQL standard. So we have made changes in the Druid itself, so that it can now provide that semantics, and we can use from the Hive, so that user doesn't have to worry about where the data, if data is stored in Druid, it will behave differently and so on. So that's on the read path. On the write path, this is also one of my favorite features which are coming into this 3.0. Now you can actually do a real-time ingestion into the Hive. And the way it works is that in the Druid tables, which you create from Hive, you can set up a spec so that it can pull the data from Kafka periodically. So that is all handled by the Druid. And then you have a Hive on top of it, so which provides you the querying capabilities. And since Druid has mechanisms to handle the real-time ingestion with its real-time nodes and the historicals and the historical data, so all of that is hidden from the user, and Hive, the queries which is coming to the Hive, they can be pushed down to the Druid, which will then query all these different nodes to get you the results. So if you have a Kafka data, it is now accessible from Hive as soon as it lands in Kafka. So yeah, there's a lot to cover here. So this is also like a big topic, and there's a talk tomorrow, actually today, on this by Nishant. So if you have more time, you can check this one out in 220B. Oops. Yeah. Asset V2. So yeah, I hinted on this in the beginning. So this is basically kind of a rewrite of the on-disk storage format that we had over past 1 year. The major change is that the updates are now basically modeled as deletes plus insert. Earlier, updates were tracked separately in their own delta files, which and then we have to, at the read time, we have to merge those delta files, and that used to take time. So now we have simplified that model. There is no more separate handling of the updates. They are just delete plus insert, and now it's much easier to do the merges of these data files when we are reading them. So this has gotten us to the performance which is at par with the non-asset tables. So now actually there's an option for you to use asset tables all the time. There's no more performance penalty on it. We have added support for load statements. So if you have some data which is lying around and you want to convert it into an asset compliant structure, that you can do pretty easily now. And also now, and lastly, we also have coming up with a new streaming ingestion library. So this is, if you want to write to the LLAP and want to write transactionally, but you are not doing your query from Hive, then you can use this library and still write in a transactional fashion. This is a library which you can embed in your application, Storm application, Spark application, and then use this to write into the asset tables. And we had this one earlier also, but the new one takes advantage of all these new features coming in, also gives you at the higher abstraction level because it handles the partitioning automatically and so on. So this is also a major revamp in the system. So that's all good. You can use asset if you have your data in the org format. But if it is not, then what to do? You still want transactional capabilities. Likely because there's some data which is generated outside of Hive and some other process is generating in Parquet or Avro or whatever. And how can make use of that? So for that, we're introducing the concept of insert-only tables, also known as micromanaged tables if you search on the Jiras. They provide the full transactional capabilities, but only for insert into and insert overwrite statements. This works for all the formats. It doesn't require any specific formats to be present. So if you have like an append-only use case where you want transaction capabilities, this might be the option to look at. This also, one implementation detail I want to highlight there is that it doesn't require any rename. So it is pretty cloud friendly, and you can get a lot of performance if you use it in the cloud environments as well. Again, there's a lot to cover here, so there is another talk on this specific topic by Eugene tomorrow, titled Transactional Operations in Hive. Yeah, so this is mostly an overview talk, if you might have noticed now, of what all work we have done and what is coming in 3.0. Replication. So I touched upon this, and this is a well-known topic, I guess, for most of you. You want your data to be backed up so that in case of a data center failure, it's possible to fail over to the other side and then restart your processing from there. So just an illustration of two data sets being in two different data centers. If one data center goes down, you want other data set to be active, the same data set to be active in the other data center, and use that to run your queries on. So the replication, a lot of work has happened in this area too. We have a new replication system. We call it REPL v2. The major highlights of it is that it's an incremental replication, meaning that we can detect what has changed in the system and replicate only those pieces. The brute force way which we used to do was to, if there is a change in partition, we're going to copy the partition again. So now we can actually figure out which files have changed and what so on, and only do the replication for that. I guess the most interesting piece here is that it's a point-in-time replication. You can think about it as like a snapshot isolation. At any given instant your other data center, the data set on the other data center is a snapshot, is that snapshot isolation from your previous, from the upstream. So which basically means that at any time you can do the failover. There is no catch-up latency needed here. And that is achieved because Hive maintains the replication state. So if your changes are happening on table A, B, C, it knows the order in which it is happening because it's sitting on the source side, and then do the replication in that order. So this allows you to get this point-in-time replication. And since it's a new implementation, we have also resolved some of the drawbacks that we had. We are now able to support functions, constraints, all of that stuff can also gets replicated, and we have also optimized the number of copies that we do. This again is a large topic, so there is another talk on it on Thursday by Shankar, seamless replication. So you can go there to learn more on this topic. So this brings me into my second last big feature of or the work which has happened in Hive 3, which is to externalize the metastore. There are too many systems, SQL systems on Hive, everyone on HDFS and Hadoop. And all of them do use Hive metastore, but we want to make it more explicit. We want to make sure that there are not multiple metastores now to support these engines, right? So Thais or Hive, of course, an example, Spark, Presto, and so on. So that's one motivation. Another is that at the same time, this processing, there are a lot of these new processing engines. There are also these new streaming engines which are coming in, like Kafka streams and so on. And they also have realized that schema is a good thing. Schema-less is not always, doesn't apply always, right? So they have this schema registry, and it also needs to be stored and used, right? So we want to unify all of that metadata storage in one place so that user doesn't have to maintain two different stores. So this basically requires, first of all, to make the metastore, to take metastore out of Hive and become a standalone metastore. So now there is actually already a module in Hive 3. The community is now working towards do an independent release of that module and subsequently take it out from Hive and make it a standalone project. So that's one piece, and the another piece is the schema registry, which I talked about. So there is work going on in that direction also to make it, to unify essentially the batch and streaming metadata. And there are more stuff happening in this area in catalogs and so on, which Alan actually going to talk about tomorrow, sharing metadata across the data lake and streams. So a lot of exciting new stuff in Hive. I have only 5 minutes left, so I will go quickly over this last piece I have, Spark LLAP. So actually, the idea is that now we have these long-running daemons. They need not to be restricted only to be used by Hive. Other services can also use them if they need to. And if they do, they get few advantages. For example, you don't have to rewrite a new reader for the ACID, right? We have changed the formats and so on. So to read the data is a little challenging. So you can use this connector to do that. You can get the security because it's all because those security policies can be applied via the LLAP and so on. So motivating factor, for example, one use case here is that in Spark to how to enable the columnar level security or the row filters. And to do that, what can happen is it needs a bunch of different technologies to be brought together. But if you do, then you can get this kind of an architecture. So so what happens here is that a client application like a Spark application can make a request to the Hive server 2. So you need to have use a new data warehouse connector that's coming up in that library, and you use that. That connector will go to the Hive server 2, will get will apply the policies by fetching those policies from the ranger, and then give back the signed plan, the splits really actually to the client. The client now can directly go to and talk to the LLAP daemons, right? There is no need. There's no need to touch AMs, Thais AMs, or Hive server 2 anymore. So your client application is a Spark application. Now has these filters applied or a column masking applied, and then they can fetch the data from LLAP daemons, and that's the one way to get these functionality in Spark pretty quickly. And there are more use cases, right? It's not limited to the Spark. Now that we have this relational view of the data node, you can use it in other contexts also. And similarly, this is a read path. And the write path also, as I mentioned, in the streaming library that we are coming up with a new version of it, that can write to these, from any application like Spark, you can write that to the LLAP directly, or from Storm, or what have you. So these are the big items, but there are lots and lots of other improvements which has happened in Hive 3. This is just a small sample of that. One of the ones which I like, which I didn't get a time to cover, was query reoptimization. So this actually lets us change the query plan in flight while it's executing. So what happens is that we had this issue earlier where if you tune the query to use the map join, which because they're fast, it may run out of memory, right? That was pretty common problem. Now what we can do, we can intercept that failure we can intercept the statistics for for the vertices which have executed, and then use those statistics to replan the query and resubmit to the system and let it to complete, and without any user intervention. So this, I'm pretty excited because it is right now we are using it just for join algorithm selection, but this in-flight re-optimization infrastructure can be used and extended for many different ways. For example, join reordering and so on. Now we have infra in place for that. Vectorization is another area where a lot of work has happened. Now we can actually do the vectorized execution on the Windows functions. We can do on more more expression types like case statements, and more data types like timestamp and date. So a lot of work in vectorization. Constraints we have introduced for data integrity purposes. Now you can define unique constraint, not null constraint, and the default clauses and so on. Real set cache is the one thing which I talked briefly earlier. Active passive HS2 HA. So this is for workload management. In workload management, you need to have a global view of the system. So you need that state to be present at one central place. That makes it susceptible for the failures, right? So in this version, we also have active passive HA for LLAP so that your queries can continue to execute. We have cache restore. So metastore server may slow down if you have a lot of metadata. Typically, a lot of partitions if they run into millions or more. So there's a work which has happened which essentially caches the metadata in the metastore daemon, and any service which is connecting to it can take advantage of that. So that's cache restore. And there are HLL bit vectors which captures the distribution of the data, which helps the compiler to make better decisions, and various other enhancements which has happened in Spark integration which I haven't kept up with. So these are just some other improvements, which is also a lot of work which has happened in Hive 3. Just to touch briefly on the future, I mean, it's all community driven. So whatever we get from the community is what gets in, but this is some of the items that we are thinking on. Standalone metastore, of course, is a one immediate goal for the project. We are working on now that we have materialized views, we can also think about making automatic recommendations for the users so that they don't have to worry about that depending on the query patterns. Better integration with the cloud storage so that Hive plays well in the cloud environments, and Hive Server 2 scalability, which is basically to enable even more parallelism and concurrency in the query. So I am out of time, but with that, thanks to the open source community for the last 10 years, and now onwards to the next 10. Thank you.